All right. We got how do we determine the redshift z by examining spectra. We'll do a little bit of lab work today with spectra and kind of qualitatively. How is redshift related to the scale factor, A of t, and the expansion of space? And so we want to kind of think about when we look at things with high redshifts, they're very distant. That's when space was smaller, that the universe was smaller than it is today. That's sort of the idea. So because the universe has been expanding, the things with low redshifts are nearby when the universe was much bigger. When we look into the distant past, that's when the universe was smaller, and the scale factor sort of captures that. So let's remind ourselves of these calculations. We'll start with how do we determine the redshift z by examining spectra. So the redshift z is equal to the wavelength that we observe minus the wavelength that we measure in the laboratory. So lambda is the wavelength. Again, just kind of going back to the very basics. You have light that has wavelength. So if I shine a light like this, all right, let's see if we can blind everybody on YouTube. All right, so that's a light that's 510 nanometers. Okay, so we can imagine. We don't have to imagine. I'll show you. Here I am, a physics teacher without a meter rule within reach. At least it's a few steps away. So 1 meter. Imagine dividing this into a billion equal sections. Each one of those would be 1 nanometer, and that color light is 510 nanometers. Okay, green light is 500, around 500. This particular shade of green, 510. I'm sorry, 532 plus or minus 10. I have sort of the insert. So that's 532 nanometers. Okay. Red light is longer wavelength. Violet light, purple light is the shortest wavelength. The visible light, even shorter than that, is ultraviolet. So we can sort of feel that with our skin. Get sunburned, but we can't see ultraviolet. Just like we can't see longer than red, infrared, right? But we can sort of heat shines in infrared, and so we can have like heat vision or infrared, goggles. We can detect it with technologies. And we'll sort of talk about that throughout the year. Every time we look at sort of a different window of the EM spectrum in astronomy, we learn, it opens up a whole new field of astronomy. There's radio astronomy, microwave astronomy, X-ray astronomy, and so on. So divided by sort of the lab value. Now, when we think about this in terms of, distant objects, the lab value is like what the, where the absorption lines are when we look at, say like hydrogen here on Earth. We're measuring this in the lab. But the thinking is like, well, that's what the wavelength, that's sort of where those emission lines would have been when the light was emitted. So remember, we're observing it after it's traveled through space, which has been expanded. So we kind of think about this as like what we're observing minus the original wavelength. The wavelength when the light was emitted divided by when the light was emitted. So this lab value, we're sort of thinking about yesterday's derivation. He worded it slightly differently, but that's sort of why. All right. So this is the shift, right? The change in the wavelength, and then we're comparing it sort of to the original wavelength. Like how much did it shift compared to the original wavelength? As a sort of a fraction of that. So that's the answer to the first part. How do we determine the redshift by examining spectra? We look at sort of where the absorption lines are, where we observe them, compare it to what we can measure in the lab, and that was where the absorption or emission line was when the light was emitted. Okay, so sort of way back in time. All right, so now we're going to think about this question: how is the redshift related to the scale factor? So remember, the scale factor is just a number that we multiply coordinates by to make things either closer together in the past, so A of t is less than 1, or further apart in the future, or A of t is greater than 1. So we define the scale factor as 1 today, so that everything just has sort of the coordinates of where they are. So we're multiplying the wavelength when the light was emitted by the scale factor. And so we're just going to kind of think about, well, when that light was emitted, we have to multiply it by the scale factor, which would have been less than 1, back then, which would have made it, space smaller. And so we're just going to sort of multiply each of these by A of t here. that in a different color. Maybe blue. So this one here, how do we determine the redshift Z by examining spectra? That's what you see in the sort of pink chalk right here. We look at the wavelengths, do this calculation, that's how we get the redshift. Now let's think about the wavelength that's observed minus the lab value, or the wavelength when the light was emitted, is going to be that sort of observed wavelength times the scale factor. That's why it's sort of different. So we're multiplying it by the scale factor A of t. And then that's over the same thing, the observed wavelength times the scale factor A of t. Here's where, when we took the sort of notes down, just kind of skipped over all the algebra. Let's take a moment to just kind of think through that and make sure that all makes sense to everybody. So we have, this denominator, so it's kind of like this lambda naught over lambda naught A of t minus this term. In other words, this is a common denominator. We kind of think about separating these out. So lambda naught over lambda naught, so like that first term, that's going to cancel out. Lambda naught divided by lambda naught is 1, right? Same thing over here, with this term, we can see that lambda naught A of t over this, the lambda naughts are going to cancel out. So then we just kind of, take a look at what does the rest of it look like then. And these all cancel. 1 minus A of t over A of t. And I think that should agree with the notes that you wrote down. Z equals this, 1 minus A of t over A of t. So we kind of check that and confirm that those are the reference notes.
Yep.
Or did I get that wrong?
It's right.
It's like, okay, pause everything and you got to start over. And then we want to do a little bit of algebra to make A of t the subject. And so sometimes it's going to be convenient to say, hey, what's the redshift if the scale factor is 0.25? Right? Sometime in the past when the scale factor would have been a quarter of what it is today. Then we plug in 0.25, we say 1 minus 0.25, which is 0.75, divided by 0.25 gives us a number, and then we say that was the redshift. Okay, so that's how we can calculate the redshift if we have a scale factor. But what if we want to make the scale factor the subject? In other words, we do this, we examine spectra, we get a redshift, and then we can say, well, what's the scale factor? All right, so let's make the scale factor the subject. So I'll do that working, I guess, right here. And,
Oh,
green. Make sure it shows up legibly. All right, so we have this equation, z equals, yeah, that's okay. So z equals this, 1 minus A of t over A of t. So we're going to multiply both sides by A of t first, and we get z A of t equals 1 minus A of t. All right, so it's multiplying this on both sides. We're trying to isolate A of t, right? So we want to get our A of t's together, right? Like combine our terms here. So if it's 1 minus A of t, and I want to get it over here, I'm going to add A of t to both sides. Add A of t. So negative A of t plus A of t is 0. So I just have 1 on this side of the equation, and I have this A of t plus this z A of t. Like that. So this plus this equal 1, right? Because this is 0. And then I'm trying to get A of t all by itself, so I need to factor it out. So like this is we're adding these two terms here, but we see that A of t is in both of them. So it's kind of like pull that out to the front, factor that A of t out. So it's like, okay, since we pulled the A of t out, what do I got to multiply A of t by to get these terms here? Well, A of t times what is A of t? A of t times 1 is A of t, right? This times 1 is itself. plus what do I multiply A of t by to get z times A of t? Well, I've got to multiply it by z, right? Z times A of t is this term. So I factored out this A of t because I want to know what it is. I'm trying to isolate that. Still equal to 1. One last step. Divide each side by this. 1 plus the redshift. So you got to do it to both sides, right? Cardinal rule of algebra. And so that cancels on this side, and now you've got A of t equals 1 over 1 plus z. And so that's how we can make A of t, the scale factor, the subject. Okay, so the scale factor is equal to 1 over 1 plus z. And those should be in your notes, right? So you don't, you kind of want to see at least once in your lifetime kind of where they come from. But from now on out, we're just going to trust that they're good equations. Anytime we need to know the redshift and we got a scale factor, use that one. And vice versa, you know, if we want to calculate, you know, the scale factor from the redshift or whatever. So now we're going to shift gears a little bit and examine some spectra. I'm going to show you that kind of what that looks like in the laboratory. You know, how we would sort of do this part of it right here. And then we know kind of theoretically how this is related. Let's remind ourselves that we already kind of said that the redshift is equal to the velocity over the speed of light as an approximation due to the Doppler shift. So we kind of understand this as a Doppler effect because the source of these waves are speeding away from us, right, with a certain velocity. So that's why they sort of stretch out. And that's why we sort of can then mathematically say, well, then that would have been when the universe was smaller, right? Space hadn't expanded yet when the light was emitted. And we have this relationship now between something that we've been talking about, redshift, and something that's going to help us understand the expansion of space in a more sort of formal mathematical way, that would be scale factor. All right? Feel free to pause and replay that as many times as you need to. You get it down. We'll see you next time.